Following on from the non-self-starting Hoynes method that we considered last time, we're going to move into and have a look at a range of different multi-step methods for solving ODEs. The first class of methods we're going to look at are the NewtonCotes methods, and they're called NewtonCotes because they're based on the NewtonCotes integration formula. So the idea with the NewtonCotes approach, and indeed with most multi-step approach, is to use one scheme as a predictor and then a different scheme as a corrector. In order to have the best efficiency, the order of both schemes should be the same, and it doesn't have to be, but you're basically wasting effort if you don't make them the same order of accuracy. Now, the predictor should be an open scheme, and the reason for that is because we don't know what the result is at the end of the interval, and the end of the interval for us here is always going to be ti plus 1. So to begin with, we have a value at ti, but we don't know what it is at the end. So we need to use some kind of open scheme that doesn't require the value at the end point. However, the corrector can be a closed scheme because we will have an estimate at the end of the value from the predictor step. So generally speaking, the predictor is open, the corrector is closed. Now, the nomenclature I'm going to use for the NewtonCotes approaches will be slightly different to what I've used before, so please pay attention. The n here is going to be equal to the number of segments minus 1. So therefore, if we have n is equal to 1, the number of segments we're going to be looking at will be 2. So let's have a look at a couple of different open methods using the NewtonCotes approach. So the two-segment approach has n is equal to 1 and has an error of order h cubed. What we're doing in this case is we're saying we're going to use these two segments from ti minus 1 to ti plus 1, so that's two segments, but the only point we're going to use is the middle point here, fi. We're going to fit a straight line, in fact we're going to fit a constant line to this, and then we're going to integrate from ti minus 1 to ti plus 1 to get an estimate of this right hand side here. And so what that looks like then is yi plus 1 is equal to yi minus 1 plus twice h times the function value at point I, so that point there. So we're integrating over two steps, but we're only using function values inside the steps. Let's have a look at the three-segment open NewtonCotes method. So we're going to use three segments, so we're going to integrate from here to here. We're going to use two internal points, that's n is equal to 2, so we're going to use fi and fi minus 1. We fit a straight line to those. Now that's no longer a constant, that can be have any slope that passes through those 2 points, and then we integrate from ti minus 2 to ti plus 1. So that's estimating the right hand side. We end up with a formula that looks like that. So yi plus 1 is equal to yi minus 2 plus 3h on 2 times the function value evaluated at I minus 1 and I. Likewise, for four segments, we have 3 points that we're going to use, fi minus 2, I minus 1 and I. We fit a parabola to those 3 points. We integrate from I minus 3 to I plus 1, and we come up with the integration formula there. yi plus 1 equals yi minus 3 times this term here. So those are the NewtonCotes open formula, where we don't know what the function value at the end is equal to. Now we're going to look at the closed methods, and again, n plus 1 here represents the number of segments, not n. So, for n is equal to 0, we have just one segment, but we have those 2 points, fi and now fi plus 1. We know what this is from the predictor step. We have an estimate of what that is from the predictor step. We draw a straight line between those two things, and we integrate over only one segment. The formula for that then looks exactly like the trapezoidal rule. So that's the NewtonCotes formula for one segment. Just a word of note, fi plus 1 is equal to the function value at xi plus 1 and yi plus 1. Of course, before we've done the predictor step, we don't have any idea of what this is, so we can't calculate f of I plus 1. So therefore, these closed methods need a predictor. They cannot be used by themselves. So you have to have a predictor first. Let's go to the two-segment case. That's n is equal to 1. We're going to fit a parabola between those 3 points, integrate over that, and we're going to end up with something down the course that looks exactly the same as Simpson's rule, because it is Simpson's rule. So yi plus 1 is equal to yi minus 1 plus h on 3 times that set of function values there, at I minus 1, I, and I plus 1. Sorry, and the error there should be h to the 5th. The three-segment case, n is equal to 2. We're going to fit a cubic to those 4 points there. We're going to integrate over that, and we come up with the formula yi plus 1 is equal to yi minus 2 plus this integral here, which of course is exactly the same as Simpson's 3/8 rule. So let's have a look at an explicit example of how we would use the NewtonCotes predictor and corrector. So the open method first, followed by the closed method. The particular method we'll look at is a method called Milne's method. Okay, there's a range of these different methods. So we're going to use a predictor, which is an integral over 4 segments. In other words, n is equal to 3. It has an error of order h to the 5th. And this is the formula that we've already derived previously. And effectively what we're doing there is we're fitting a cubic over the 3 points fi minus 2, fi minus 1, and fi, integrating that from ti minus 3 to ti plus 1. That's what gives us that formula. So this gives us an estimate of what y is at this point here, and we can calculate the function value there, fi plus 1. We then use a corrector, and the corrector we only need n is equal to 2, because that gives us an error order h to the 5th as well. So we then use Simpson's rule. This is the corrector step, which looks like that. And I've already mentioned this, but it's important that the predictor and corrector have the same order of error, otherwise you're wasting effort in one of the steps. So these kinds of schemes allow us to not have to take multiple guesses within a time step. For example, as you have to do in RK4, this allows us to use information that we've already calculated in the past and come up with an estimate that has a good order of error, for example, order h to the 5th. So those are the advantages of these NewtonCotes predictor-corrector methods.